So this last part of the chapter is about something called Gibbs free energy. Gibbs free energy, the main idea of this is that it takes into account both entropy and also temperature and heat of the reaction, in other words, enthalpy, and it allows us to predict whether a reaction will proceed or not, meaning whether it's going to be spontaneous at those specific temperature and pressure, whatever it happens to be at. So it's at specific conditions, will this reaction occur? So it takes all these things into account. So even though you have like a very positive entropy, so an increase in entropy, which the universe likes, you can have certain cases where the temperature affects it so much, or the pressure, and you end up not having a spontaneous reaction. So this allows us to take into account heat of the reaction, in other words, pressure also, and also temperature, as well as the entropy. So it's often called like the chemical potential, like whether the reaction will happen. If delta S universe, so the entropy overall of the universe is positive when spontaneous, then the delta G should be negative. So for entropy, a positive entropy is good, right? It means spontaneous. For delta G, we want a negative delta G for spontaneity. So I'm going to take you through a few situations where we will have a negative delta G, in other words, a spontaneous process. So delta G will be negative when delta H is negative, meaning it's exothermic. And when delta S is positive, meaning that entropy is increasing and you have overall more randomness. Another situation where you will have a negative delta G is when your enthalpy change is negative, again, and large. So that would help a process where even though the delta S is negative, meaning you have less entropy, which the universe doesn't like, the fact that you have a very large and exothermic reaction kind of compensates for it. So you see how you can have different situations where although, you know, this thing is very small and the universe doesn't like it, or this thing is very negative and the universe doesn't like it, overall it can add up to where the universe, the process will happen spontaneously and the universe will like it. Another situation is when you have a delta H that is positive but small and your overall entropy is very large and positive, or you have a high temperature. Delta G will be positive when delta H is positive and delta S is negative. This is decreased randomness, which you know the universe doesn't like, and this is an endothermic reaction. So for these specific conditions, you will never have any spontaneity at any temperature. And then finally, when delta G equals 0, this means the reaction is at equilibrium. There's no favoritism versus like going forward or backwards. So at equilibrium, you have equal rates of forward reaction and also reverse. And whenever you have this situation, delta G is overall 0, like everything cancels out basically. And it also makes sense in terms of spontaneity and reversibility. Remember we said that spontaneous reactions are irreversible or not reversible. So that's why you have an overall spontaneity for, you know, one-way reactions. Whoops. Pretend that's one arrow. One-way reactions versus for equilibrium reactions you have both ways. And that's why overall you get a 0. So here are those situations that I was talking about, and you have some examples along with it, along with the temperature dependence. So I would say kind of take some time to kind of write this out, maybe say it out loud to yourself, like explain it to yourself, because just listening to it may not just click right away. And by explaining it to yourself, I mean using the terms that you already understand. So for example, a negative delta H means you have an exothermic reaction. Exothermic reactions give off heat. A positive delta S is positive entropy, more randomness, the universe likes this. So overall, you will get a spontaneous reaction no matter what. whether it's at high temperature or low temperature. The universe overall likes both of these conditions, and because they're both, you know, the ideal signs, then overall you'll get a negative delta G. So kind of explain it to yourself in that way, or write it down, summarize it along with the rest of these situations. Notice that in these two situations, you can have spontaneity depending on the temperature. So there's temperature dependence right there. This is another very similar chart, except it kind of actually like lays it out in terms of temperature, I think, better. So for example, here when you have a negative enthalpy and a positive entropy, it tells you in this particular case with these two conditions, process is spontaneous at any temperature, and then the opposite is true for the opposite signs, and then these are the ones that are temperature dependent. So it's just a different graphic, but it overall shows you the same four scenarios. In this example, we will be predicting the temperature dependence of the spontaneity. So we have to think about two things. Remember that delta G depends on, or delta H minus T delta S. So we're trying to figure out whether it's going to be temperature dependent or not. As we saw in the previous graphics, we have two situations where you have temperature dependence, and then two situations where you don't have temperature dependence. One will be spontaneous at all times, one will be non-spontaneous at all temps and times. So that's what we're going to figure out. We're going to figure out what's going on with delta H and delta S. So here, for this reaction, we have an incomplete combustion of carbon. So the key word here is combustion. And the key word is combustion because combustion reactions always give off heat. Combustion reactions are basically like anything reacting with oxygen, and typically you'll see fire from it, from all the heat given off. So heat is released, which in other words means you have a negative delta H. So a lot of information with just one little word right there. And then we're overall looking at the spontaneity and whether it's dependent on temperature. So something to note here is how many moles of gas we are starting with and ending up with. So remember that anytime you form more gas or more liquid, those are more higher entropy compared to solid or the previous phase, whatever it is. So gas is always favored in terms of entropy. And here we're starting off with 1 mole of this gas, and we're ending up with 2 moles of this gas, of a gas basically. And because of that, we are going from a lower entropy on this side to a higher entropy. So what we have here is a negative delta H and a positive delta S, because we're going from lower moles of gas to higher moles of gas. This situation will mean that you are spontaneous at any temp, which means it is not temperature dependent. So let's say I give you this type of question, and a very similar type of question for a multiple choice question. Then I would be, for the answer choices, I could say, is this temperature dependent? Or I could give it as a true or false, right? I could say this is temperature dependent, and you would have to figure out, okay, what is the delta H, the sign going to be, what is the delta S, what's going on here? So then you would tell me, okay, true or false, depending on what statement I made. So that is a way that I can ask this, where I'm testing this concept. And this is just like in general terms, you know, we're not actually calculating anything, we're just predicting based off of what information is given about this reaction. Before we go into calculating overall delta G changes, I do want to discuss what these values that you're going to be seeing are. So we have something called the free energy of formation, which is delta G, and you'll see the little F and then the little naught. The little naught again means that you're at standard conditions. This is the change of free energy when 1 mole of compound forms from its constituent elements in their standard states. The free energy formation of elements is 0. So notice how these diatomic elements, that's how they exist in standard states, is 0, along with, for example, carbon. Its standard state is always graphite. Everything else is a compound, so they all have delta G's associated with them. So these values have already been recorded, and we can use them to calculate overall changes. So because delta G is a state function, this is useful to us because similarly to delta H, and also we just learned about how delta S, we can do the same thing. We can overall sum up delta G values of individual reaction. So individual reactions have their own delta G's. We can sum them depending on what we need, and by what we need, I mean usually an unknown. And you will manipulate however you need them to be, however you need them to look, and you can add them up, and this will give you overall delta G of the reaction. So similar rules apply where if a reaction is reversed, you will flip the sign of the G. If the number of moles of all of the reactants and products needs to be divided or multiplied by something, then the value of delta G is also multiplied by that same value. So delta G again is also similarly to delta H. It's extensive, so depending on the amount, you have to also take into account how that changes the delta G. So knowing that information, we can now talk about how we can calculate delta G. So at 25 degrees C, which is standard conditions, we can find the overall delta G of a reaction by determining the delta G's of the products, subtracting away the delta G's of the reactants. So for any state functions, you can typically do this. And then for any other temperatures other than 25 degrees C, you have to take into account whatever temperature that is. So that's why you have to not type this in, but fill that in specifically into this delta G equation. So you would calculate this, plug in that temperature, you get the delta G of the reaction. So in this example, we will be applying what we just talked about. We'll be using these standard free energies of formation and also our delta H, so our enthalpies of formation and our absolute entropy values that we have listed. We're going to use these and we're going to calculate the overall delta G in two ways, the two ways that we just discussed. So we can calculate it this way, which is basically what the instructions say for A, and then B. And we're going to do both of those. And we'll see, hopefully, that we get the same answer, because we should get the same answer. So for this first method, we're considering the decomposition of yellow mercury 3 oxide. So we have mercury 3 right here, mercury 3 oxide right here. It's decomposing into mercury liquid and half a mole of O2. Remember, for any of these types of reactions, typically they're called thermochemical reactions, we can have occasionally some fraction coefficients. This is only for these types of equations. For all other equations, we will typically keep it, as full integers. But here, in case you see that, don't be alarmed. It's just for these particular reactions. So method A tells us we are going to take the overall delta G's of the products and then subtract away the delta G's, the sum of them, of the reactants. So we have them listed here. So all we have to do is make sure that we multiply times the correct amount of moles. So first I'm going to take the products, I'm going to put it in brackets to make sure that I don't confuse any parentheses with the reactants or anything. So just for organization. So we have 1 mole of liquid mercury, and luckily it's easy, it's 0 kilojoules per mole for this delta G. So that's easy. And then we're going to be adding half a mole, and again, of O2 gas, which is again 0 kilojoules per mole. So that's pretty easy. Overall, that equals 0. And we are going to subtract away that 1 mole, again, you can put this in parentheses, of our reactant, which is our mercury 3 oxide. And here, this does have a value for it. So it's negative 58.43 kilojoules per mole. So in this case, we would have a value. So overall, this side equals 0 minus 58. Oh, let's be careful with that. I was about to get caught in that trap. It's minus a negative 0.43. So overall, kilojoules. Overall, this would give me positive. So just be careful with the signs there. Don't omit any, because then potentially you could type something wrong or write something wrong. So that is our delta G that we got overall for this reaction using the standard delta G's formation. So now we're going to try method 2. This one's a little bit longer. So we are going to first find our delta H. So we have to do the products minus the reactants for delta H. So let's go ahead and do that. Luckily, again, everything is 0 for the products. So I'm just going to write 0 kilojoules per mole. Like, sometimes it is easier to just work smarter. You know, obviously I'm doing this because we've already have a lot written going on. But for your own notes, yeah, probably write it out if you're just starting out with these types of problems. So we have our products right there, 0 minus our reactant, and again, that's only 1 mole of that reactant, so we don't need to multiply it by anything. So it's going to be minus negative 90.46 kilojoules per mole. So you end up getting positive 90.46 kilojoules. So from here, this is our overall delta H. So I am going to erase some of this up here, what we did for part A. All right, I got some space now. So all I left here was the delta G we got for part A. So that's what this is right here. So we have our delta H. Now we need to calculate our delta S for part B. So we have to take, again, our products minus our reactants, and remember absolute entropies, they're always positive for anything, regardless of even just elements by themselves at standard state. So that's why you do have values for this one, for the standard state elements. So similar process, we're going to take the products, and now we actually do have to take into account those moles because we do have values. So 1 mole of Hg first, and the value for it is 75.9, and this time it's joules over k mole. And put this in brackets, plus the half of a mole times our O2, which is 205.2 joules over k mole. And then from this, we will subtract our reactant, and luckily it's just 1 mole, times 71.13. Okay, so, make sure you punch that all correctly into the calculator. You can do 1 step at a time. And then the overall value you should get for this delta S is 107.4 joule over mole K. Okay, so now we have both our delta H and delta S. Now we can go ahead and plug into our equation. So I'm going to move a little bit more around. So we know our delta G for this one was 58.43 kilojoules. So I can go ahead and make some more space again. Okay, cool. So again, now I'm going to plug into this equation right here. So we know that we have room temp. Room temp is 25 degrees C plus the 273.15. That gives us 298 90.15 for our temperature. So we have our delta H, 90.46 minus T, 298.15 Kelvin, times the delta S, which is 107.4 joules. Oh, it should just be joules over mole. Oh, so we need to convert something. So one of these needs to be converted. So we can attach to this at the end. We're going to multiply against this, this portion right here. We're going to multiply this. 10 to the third joules. So it's something more like that. 10 to the third joules is 1 kilojoule. So just make sure to divide by 1,000 on this term. And overall, I know this is kind of messy, I'm sorry. Overall, you should end up getting, of course, that 90.46 kilojoules per mole minus 32.01. And notice how that K is what cancels that temperature out. And then kilojoules per mole. And for your final answer, we should get 58. Yeah, 90 minus 32 sounds about right. Kilojoules per mole. And notice how it matches the other one we calculated. Obviously, one of these was a lot faster, but you can do both. So depending on what information I give you, just make sure to show me the work for it. So let's say on a problem I told you using the standard Gibbs free energy changes, calculate the overall change for this particular reaction. Or I could say using the standard enthalpies of formation and the absolute entropies, calculate the delta G. So depending on whatever I give you, but I like this problem because it shows you both and it shows you how they both end up being the same value.